Welcome back, AP Stat, to another round of boot camp. This is boot camp number 3 for your response. These are problems from the 2019 AP Stat exam, if you are curious. The sizes in square feet of 20 rooms in a student residence hall at a certain university are summarized in the following histogram for problem number 1. Part A reads, based on the histogram, write a few sentences describing the distribution of room size in the residence hall. Remember our CUS model: center, unusual features, shape, and spread. See how you do with part A, pause the video, and unpause the video when you're done. Okay, here's part A. The median of the distribution is somewhere between 200 and 300 square feet. All right, so there's a measure of center that'll work for us. There are 20 values. The median would be the mean of value 10 and 11. Value 10 is the only one right here, and value 11 is somewhere in here, so somewhere between 200 and 300 square feet will do it. There don't appear to be any outliers. The distribution is bimodal, roughly symmetric, and the range of the distribution is between 150 and 250 square feet. And to be clear, that doesn't mean the values range from that. The range is just the highest value minus the lowest. So if the range of the distribution is 250 square feet, that means we have a value really close to 350 and a value really close to 100 for our highest and lowest values. But if the range of the distribution is 150, well, then the lowest value would be close to 150 and the highest value would be close to 300. So somewhere between the furthest extremities of the highest and lowest bar and the closer extremities of the highest and lowest bar, that's going to be our range. And range is a good way to measure the spread of data here. Okay, so part B. Summary statistics for the sizes are given in the following table, all right? So we have this table right here, and we would say determine whether there are potential outliers in the data. Now, we said there didn't appear to be outliers. We're going to check for absolute certain, and then we're going to use the following grid to sketch a box plot of room size. Okay, give part B a go. All right, I'll assume we're ready to continue. Here comes part B. So the IQR, interquartile range for the data, is 292, that is Q3, minus 174, that's Q1, is 118. Now, we'll note that there are no rooms 315 plus 1.5 IQRs. There's no rooms above that in terms of square feet. There are also no rooms below 134, that's my lowest value, minus 1.5 IQRs, okay? Obviously, because we would have negative square footage, all right? So that's not going to happen. So there we go. There are no outliers. Here is a box plot. You'll see we have the lowest value. We have Q1, Q2, Q3, highest value. That ought to do it. Letter C. What characteristic of the shape of the distribution of room size is apparent from the histogram but not from the box plot? Think about this, give it a go on your own, and unpause the video when you want to check your answer. All right, here comes part C. From the histogram, we can see the distribution is bimodal, right? There is no way of knowing that from the box plot alone. Here comes problem number 2. Researchers are investigating the effectiveness of using a fungus to control the spread of an insect that destroys trees. The researcher will create 4 different concentrations of fungus mixtures. We have 0 milliliters per liter, 1.25, 2.5, and 3.75. An equal number of the insects will be placed into 20 individual containers. The group of insects in each container will be sprayed with one of the 4 mixtures, and the researchers will record the number of insects that are still alive in each container 1 week after spraying. For part A, we need to identify the treatments, experimental units, and response variable. See if you can do this on your own. Pause the video and unpause the video when you want to check your answer. All right, here comes part A. The treatments are the sprays with the 4 different concentrations of fungus. All right, you have these 0 milliliters per liter, and we'll see that one in just a moment. 1.25, 2.5, and 3.75. The experimental units are the 20 containers with insects. Note, the experimental units are not the insects. They are the containers that have an equal number of insects. Okay. The response variable is the number of insects alive in each container a week after spraying. That should say container, not contain. All right, now let's look at part B. Does the experiment have a control group? Explain your answer. All right, let's see if we can explain our answer. The control group is the set of containers that are sprayed with 0 milliliters per liter of fungus spray because, of course, there is no fungus present in the spray. All right, let's look at part C. Describe how the treatments can be randomly assigned to the experimental units so that each treatment has the same number of units. I guarantee you've done several problems like this up to this point. So you know that there are a bunch of different ways to do this. Try your hand at this one. See if you can do part C, and then check your answer once you are done. All right, let's look at part C. Here's my answer. We can label each container with a unique integer from 1 through 20. And we're going to use a random number, generator to choose 15 integers. The first 5 will receive the 0 milliliters per liter treatment. That's the control. The second 5 are going to receive the 1.25 milliliters per liter treatment. The third 5 are going to receive the 2.5 milliliters per liter treatment, and you got 5 left over, and they have been effectively randomly chosen to receive the 3.75 milliliter per liter treatment. Okay, let's look at number 3. A medical researcher surveyed a large group of men and women about whether they take their medicine as prescribed. The responses were categorized as never, sometimes, or always. The relative frequency of each category is shown in the table, and I am not going to bore you to tears by reading all those values. Part A. One person from those surveyed will be selected at random. We got little Roman numerals 1, 2, and 3. Let's start with number 1. First, what is the probability that the person selected will be someone whose response is never and who is a woman? Number 2. What is the probability that the person selected will be someone whose response is never or who is a woman? Notice the words I'm emphasizing. Number 3. What is the probability that the person selected will be someone whose response is never given that the person is a woman? Okay? Give this a go on your own. Try 1 through 3. They're all going to be a little different. Pause the video, try it, and unpause when you want to check. Okay, let's look at our answers. Probability of never and woman is 0.0636. You literally just have to read this cell right here and you got your answer. How about that for a free point? Probability of never or woman, all right? Probability of never or woman. Well, that's going to be 0.12 plus 0.53 minus little Roman numeral 1's answer. Now, how do we get that? Well, we want to consider all the ways in which we could get a result of never, and we want to see the proportion of women, okay? But if we were to put those together, we're double counting one of the cells. We're double counting the intersection of never and women, which we found for part A, Roman numeral 1. So we need to subtract that out. Very good. And we have our answer. Now, the probability of never given woman is going to be equal to the probability of never and woman, again from part Roman numeral little 1, divided by the probability of woman, which we have found right up here. Doing that division, we get 0.12, and that is going to play a role in just a moment. Part B. For the people surveyed, are the events of being a person whose response is never and being a woman independent? Justify your answer. Now, I told you that you can use Little Roman numeral 3 to help you. See how you can use Little Roman numeral 3 to show whether or not those two events are independent for Part B. Okay, I'll assume we're ready to see this answer. Well, the probability of never is 0.12. And the probability of never given woman is also 0.12, which we just found. So the odds of never and the odds of never given woman are the same. That means that the odds of never do not change whether we are considering only the instances in which we are given woman or if we're not given woman. In other words, it doesn't matter whether woman is part of the equation here, so we can assume that those events never and woman are independent. Being a woman is independent of the response of never. There you have it. Okay, let's look at Part C. Assume that in a large population, the probability that a person will always take medicine as prescribed is 54%. If 5 people are selected at random from the population, what is the probability that at least 4 of the people selected will always take their medicine as prescribed? Support your answer. All right, try Part C. Think of a particular probability model that you could use, maybe a calculator function. Maybe you've seen a problem like this before in a free response section. Hint, hint. Give it a go. Unpause when you're done. All right, I'll assume we're ready to continue. So we're going to define our variable here and state its distribution, okay? So we're going to let x be the number of people out of 5 who always take their meds as prescribed. X then fits a binomial model. We have 5 trials, and the probability of success is 0.54. So, probability x is greater than or equal to 4, that means that there are 4 or more people who say that they always take their medicine as prescribed. I'm going to actually use the complement of the event. I'm going to say that's 1 minus the probability x is less than 4, which I could write as 1 minus, we can use good old binom CDF here. Now there's another way of doing this. It uses the formula for the binomial probability model, but I like binom CDF here. We have 5 trials, probability of success is 0.54, and we're finding the odds of 0, 1, 2, or 3 successes. Add them all up, subtract that from 100%, and we get our answer, 0.24149. That's one way to do it.